In our last video, when tasked with analyzing the physics of the interaction between electrons, positrons, and photons, we determined that the set of possible events was limited by the so-called laws of conservation. That is to say, there's a set of quantities, like energy, momentum, and charge, which don't change even when the underlying state of a system changes. Hence, the system can only undergo transitions which keep these numbers fixed. Among those transitions that do satisfy the laws of conservation, however, quantum physics has told us that nature does not discriminate. All are fair game, and even the most seemingly unlikely events occur with some non-zero probability. The conventional wisdom uncovered here is typically communicated through the old adage, every event that can happen, that is, every event that respects the laws of conservation, will happen. Introduced in this way, the laws of conservation seem essentially arbitrary. You're probably thinking, why can't these numbers change? Both in the sense, why are there any numbers in nature that don't change, and why are they these specific numbers? It turns out that the answer to this question has everything to do with something you probably learned about in elementary school: geometry. Very broadly speaking, geometry is the study of shapes. Suffice to say, there are many different kinds of shapes, but for the time being, we can consider just two: circles and squares, nice and simple. Visually, distinguishing between these two kinds of shapes is a breeze. Circles are, well, round, circular, and squares are, boxy, square. But let's take a moment to develop a somewhat deeper appreciation for what we mean when we say these things. First, let's draw a circle and a square on a piece of paper. Then, let's start rotating the paper. We can rotate the paper by any amount that we'd like. Depending on the amount that we've rotated by, the square might look like itself, but more likely than not, it'll appear to be standing on one of its corners rather than on one of its edges. On the contrary, the circle will always look exactly the same. Indeed, we have uncovered the very defining characteristic of a circle. Under any rotation, its image is unchanged. In fancy language, the circular geometry is invariant under rotations, and therefore the circle is said to be rotationally symmetric. Well, okay, that's cool, but you knew all this, so you're probably thinking, what does it have to do with laws of conservation and particle physics and the Standard Model? Well, everything. You see, while on one hand the circle is defined by the fact that it's rotationally symmetric, on the other hand, an object that is rotationally symmetric must be a circle. That is, if we were to ask you to draw a picture that did not change no matter how much you rotated it, you'd be forced to draw a circle. In this way, imposing a symmetry on the drawing reduces the degrees of freedom of the artist. Nature is the same way. When a physicist performs an experiment with a determined outcome, it does not matter at what time of day or what location in space the experiment is performed. It will always turn out the same result. Put in a more suggestive way, the laws of nature do not change through time and space. Even more suggestively, the laws of nature are invariant under translations through time and space. And finally, the laws of nature are translationally symmetric. From our experience with circles, we know that imposing a symmetry on a drawing reduces the degrees of freedom of the artist. Well, here, the drawing is the physics of a given system, and the artist is Mother Nature herself. If we want the laws of nature to be translationally symmetric, we need to give up the ability to define some of the aspects of the system. In particular, there are 3 dimensions of space and 1 dimension of time. Thus, we must give up the ability to determine 4 numbers associated with the system. In the case of translational invariance, these numbers are the momentum in each direction, up, down, left, right, forward, and back, and the total energy. Stated concisely, translational invariance leads to the conservation of momentum and energy. Okay, that's pretty cool, I know. But the question still remains, why does translational invariance result in energy and momentum conservation? And what about all the other laws of conservation? Don't worry, the physicist is nothing if not thorough. In our next video, we'll make the relationship between symmetry and conservation concrete, and provide a method for determining all of the conserved quantities associated with a given system. But, for now,